Hello everyone. Today I'm going to discuss about Apache Hadoop. The first thing in Apache Hadoop is facts. Hadoop is an open source technology which is under Apache license, and as it is an open source, there are committers from different companies. The point to be noted is there are about 40 core Hadoop committers from more than tech giants like Cloudera, Yahoo, Facebook, Apple, etc. There are 40 core Hadoop committers, and there are more than hundreds of contributors which are giving support to the Hadoop, like fixing the bugs and creating the features, etc. Hadoop is not only a single technology, it is a mixture of applications, tools, and related projects. Hadoop has a very large ecosystem which consists of Hive, Flume, HBase, etc. I'm going to discuss about Hive, HBase, etc. in the further slides. Who uses Hadoop? If it is a small technology, it will not be used by the tech giants. You can see there are many giants listed here like IBM, Samsung, eBay, Netflix, Groupon. These are very big companies which are using Hadoop, so we can understand that it is very reliable and it is very efficient. It also supports vendor integration like Teradata, Jaspersoft, Netezza, etc. It is very easily integratable with all the vendors. Coming to Cloudera, Hadoop is a technology, but Cloudera is a commercial company which manages the Hadoop. It was established by people working from Facebook, Google, etc. So you can understand the quality of the product from the people who established that. Cloudera provides consulting and training services for the Hadoop users. And Cloudera also contains committers to the Hadoop. So it is more of a kind of developers as well as trainers. Now coming to the software, Cloudera has its own distribution to Hadoop, which is a package. It is very easily installable, and it always releases with the stable version of the Hadoop. There is no beta and alpha versions. It consists of the stable version of Hadoop. As it is stable, it consists of very less or none bugs. So coming to the components, it consists of Apache Hadoop, Hive, Pig, HBase, Zookeeper, OZ. Coming to Hadoop, it is the core technology, and Hive. Hive is a data warehouse. It's like a warehouse where all the data is being stored, and it is used for summarizing the data, querying and analysis. It's like an SQL over the Hadoop. And coming to the HBase, it is an open source non-relational database. It is also a distributed database. So it has its own file system, which is Hadoop file system, HDFS. And coming to the Zookeeper provides operational services for the Hadoop cluster, like maintaining the clusters and the nodes, etc. These all are being taken care by the Zookeeper. And Uzi is a workflow. It's like a job scheduler. So whenever you want to run jobs and schedule the jobs to run at a particular time of the day, Uzi takes care of those things. And coming to the platform, this is the architecture of the Hadoop, in which the bottom layer is coordination. As I mentioned, all the operational services are maintained by the Zookeeper, and the coordination is maintained by the Zookeeper in this layer. And the above layer consists of the core Hadoop, above which we will be writing our own technology, which is the language and compilers. It can be either in the Pig or in the Hive. And as I mentioned, HBase is a non-relational database, so the files are stored in the form of HDFS. So the read and write access is pretty fast in the HBase. And the data integration is managed by Flume and Scoop. Coming to the scheduling, as I mentioned, Uzi is a job scheduler, so it handles the scheduling. And the metadata, as Hive is the data warehouse, it manages the metadata. Workflow, the job workflow, it's again maintained by Uzi. The UI framework, it can be of any technology. It is maintained in the Hue, and its corresponding SDK is in the Hue SDK.
So in the traditional computing system, compared to Hadoop, it can only handle small amounts of data. And for decades, we have been focused on increasing the processor and RAM, to increase the computing power of machines. One way the traditional computing system address these challenges is through distributed processing. So a single job is split into different and is processed by different machines. So, for the problem associated with the distributed computing is that it has a very complex programming that we have to deal with the synchronization, its use, bandwidth, dependency, and all. So the programming of distributed application and systems are really complex. And of course the data storage, data has to be copied to and forth, so there is a bottleneck on the data as well. And the and in today's world there is huge amounts of data, and these conventional traditional computing systems may not be able to handle it. See, even Yahoo, Facebook, and all have 170 terabytes of data. So the data becomes the bottleneck. So it's no longer processing power. We have the processing power, but there is huge amounts of data, and how to deal with this data is a difficult thing. So the system has to support the partial failure of a component, and it has to recover from those things also. That recoverability deals with that, and the component recovery. So if a component fails, it should be able to rejoin the systems when it is recovered. So there is also consistency. So if a job fails, it should not affect the outcomes of the job as well. So there is also scalability issues. So Hadoop is based on the work done by Google. So it takes a radical approach in solving the problems. So nodes talk to each other as little as possible. Applications are written in high-level code. Data is spread among machines in advanced. When data is loaded to the system, it is split into blocks, and these blocks are processed. And if a node fails, the master will detect that failure and reassign the work to a different node on the systems. And and if the system and fail node restarts, it is automatically added back to the systems and assigned to new tasks.
So, as a software framework, Hadoop is composed of numerous functional modules. Two of them, as I mentioned, are HDFS and MapReduce. Now, HDFS is the part that is responsible for storing the data into the cluster, and the MapReduce is the part that is responsible for processing the data that is already stored in the cluster. The way HDFS works is that it splits the data into blocks, basically splits each file into blocks, and then distributes those files, those blocks, across multiple nodes in the cluster. Now, our nodes are basically cheap, unreliable computers, but then you have multiple copies of these blocks, of the same block, stored in different nodes, and hence you get some reliability and availability leverages out of this. As I mentioned, the MapReduce part is responsible for processing the data. And then, as obvious from the name, it has two phases. First the map part and then the reduce part. Basically, the MapReduce tackles large distributed data processing with first mapping every individual block, that is applying a task on every individual block, and then after all the maps are done, all the maps are applied some tasks to them, then it passes this intermediate data to the nodes which perform the reduce part, that is aggregating all the intermediate data and outputting a single result based on those. Now, the best case for Hadoop is when we have um, like millions of files, each of size of typically 100 megabytes, and then it's considered a modest number of large files. So this is the case that Hadoop really produces the best results. So these files, as I mentioned, are stored in blocks, and they are write once, meaning that there is no option to access the files and to write the files randomly. And then it's basically optimized for streaming data reads. So random data reads doesn't really work well on HDFS. Now we have, as I mentioned, we have multiple copies of each block in different nodes. And then the default in Hadoop is that it stores every block of data in 3 different nodes. And I assume you can change it, but this is the default. And this is the basic component that makes it reliable and available. So one of the nodes that are in our Hadoop system, our Hadoop cluster, is called a name node, and basically contains the metadata of the entire other nodes that exist in the cluster. And the name node basically includes the data of what block of data is stored in what node. And then for retrieving the data, what we need to do is first to go to the name node and then get the metadata about the block of file or the file that we are interested in. And then after we get the information on which nodes contain those blocks, we can just go and fetch the data from those specific nodes. Now to get data into or out of the HDFS, there are a couple of ways. One of them is the Hadoop API. The other one is the ecosystem projects that I already mentioned, projects like Flume or Scoop. Flume is basically, as I mentioned, a tool for collecting and aggregating the data and moving those in streaming data into HDFS.
Let's now quickly take a look at the Hadoop ecosystem. And we'll start off with Hive and Pig. So we do know that Hadoop has HDFS and MapReduce at its core, and the ecosystem basically consists of projects that are built around this core. And look at Hive and Pig. So Hive and Pig were basically developed by Facebook and Yahoo respectively in order to enable their existing data analysts and programmers to take advantage of the MapReduce feature that's available as part of Hadoop. So you can see that Hive is SQL-like and Pig has a data flow structure. This depicts the difference between Hive and Pig. We now look at HBase. So HBase is the Hadoop database, which is a column family store database layered on HDFS. It can store large amounts of data and has very good write throughput and has a constrained access model. You can see the difference between the RDBMS and HBase in this slide. And this depicts how the column family exists as part of HBase. This is a use case by WordLingo, and they use HBase as part of their existing system. So HBase is used when you want to have random writes, random reads, or both, and you need large amounts of data to be stored, and you have well-known patterns which you access. And of course, you don't use HBase and you go for a traditional system when you just append to your data set and reuse that data set over and over again. And you primarily do ad hoc analytics. And of course, if your data fits on a single node, then you don't require HBase. Now we look at Flume. And Flume is a distributed, reliable, available service for efficiently moving large amounts of data. And it's developed by Cloudera and provides scalability, manageability, extensibility, and reliability. So the design goal is to continue delivering events in the face of system component failure. It scales well, and it has a master controller for manageability and can be extended by adding connectors. The master holds a configuration for the node, and the node will communicate with the master every 5 seconds and pass on a version number. And if the version number is older, then the node is advised to reconfigure itself by the master, and the master provides the configuration information to the node. This is an overview of a Flume system. And we have other projects as well, such as Scoop, which is a SQL to Hadoop converter. And it extracts data from RDBMS and inserts that into HDFS and provides command line interface as well. It's developed by Cloudera. And these are some of the partners for developing connectors. Oozie provides a way for developers to refine their entire framework, so they can define if jobs need to run in parallel or wait for certain other jobs to finish their tasks, and are written in XML. So Hue is a graphical front-end interface for developers and administrators, and it's developed by Cloudera as well. This is a screenshot of Hue. And to conclude, we've gone through an introduction. We've seen Hive and Pig, HBase, Flume, and the existing projects that are available. So thank you for watching, and please do take a look at more resources online.